Namaste students, welcome back to Rama Teaches You. Today we are going to do IB Physics video number 4. Okay, in this section, the previous section we had already discussed the Millikan's oil drop experiment. Okay, the way Millikan was able to find the charge on one single electron. Okay, by using his oil drop experiment, he found the charge to be 1.6 into 10 to the power minus 19 coulombs of negative charge. Okay, we have discussed force, field, potential, and potential energy. Now, let's do some questions regarding these. Okay, so worked example number 11. In Millikan's experiment, a negatively charged oil drop is introduced into the space between two parallel horizontal plates. Okay, when the electric field between the plates is switched off, the drops fall vertically, reaching a constant speed of 0.23 millimeters per second. Okay. Introduced into the space between. Okay, when the electric field between is switched off, the drop falls vertically downwards. Okay, draw a free body diagram showing the forces acting on the drop. There will be a force of weight that is acting vertically downwards, right? And basically the viscous drag which is acting vertically upwards. Okay, and yeah, the weight W of the drop is balanced by two forces acting upwards, the buoyancy force and the viscous drag force, because I saw this viscosity of air. Okay, because of this viscosity of air I became curious that, oh yes, they are trying to basically also consider the viscous drag force also. So what is buoyancy? Buoyancy is the upward thrust that you feel, right, whenever you are basically inside a fluid. Air is also a fluid, therefore it will have both the buoyant force as well as the viscous drag. And how do we know that drop this drop of oil is in equilibrium? It is in equilibrium. That means all the net forces acting on it is equal to zero, because it is not falling with a constant acceleration. It is falling with a constant speed, right? It is falling with a constant speed. If it were falling with a constant acceleration, then we would say that, oh yes, there is a net force that is acting downwards. But no, it is not happening like that. The viscous force, basically the viscous force and the buoyant force are able to cancel out the gravitational force, thus allowing the drop to fall much more freely towards the ground. Okay. Okay, fine. So these are the two forces. We have the buoyant force, we have the drag force, and the weight. Okay, next. Um, Determine the radius of the drop. If the density of oil is this much, the density of air is this much, and the viscosity of air is 1.8 into 10 to the power minus 5 Pascal second. Okay, fine. So the net force on the drop is zero. Hence, the F downwards, the downward force is equal. Sorry, no, the FD, the drag force is equal to work done. No, sorry, the weight minus the buoyancy. The weight minus the buoyancy basically equals the FD. Okay. Now, substituting the expression, basically you could have just written it like this: FD plus B is equal to W, or FD is equal to W minus B. This one single line would have explained a lot. Substituting expressions for the individual forces in terms of R and V. So we know the viscous drag force is 6 pi nRV, right? 6 pi. N is what? The coefficient of viscosity. R is the radius. V is the velocity. 6 pi nRV is equal to, we know the buoyant force. What is the buoyant force? The buoyant force is equal to the basically the weight of the liquid displaced, right? Yeah, the density of oil minus the density of air. The downward minus the upward. The density of oil minus the density of air. So basically, we know that density is equal to mass upon volume. Therefore, mass is equal to volume times density, right? We know the volume of the sphere. The spherical oil is 4 by 3 pi r cubed rho. Rho is what? Rho is going to be the density of oil multiplied by G. So this is going to be mg. This is the mass of the oil that is going downwards. Okay, and what is the buoyant force? The buoyant force is equal to, now F buoyant is equal to 4 by 3 pi r cubed density of air into G. Now, basically, the downward force is basically equal to what? The oil minus this much. Okay, so we will get 4 by 3 pi r cubed density of oil minus the density of air multiplied by G, and now the weight also, right? Then we have the weight of the oil drop also. Do we? No, no, we don't. We don't. Basically, this is it. This is representing the weight of the oil only. This is what's representing the weight of the oil. The understood, the mg basically 4 by 3 pi r cubed density of oil minus density of air, because it is going downwards. Now we have the forces provided by us. So what can we do? See, Akshay, this 4 by 3 pi r cubed density of oil is the downward force, minus 4 by 3 pi r cubed density of air multiplied by G is the buoyant force. Understood? Now, basically what we can do is we can cut the two r's from both the sides. We can cut the two r's, right? This r and this r cube becomes r squared. So basically r square is equal to this much, r is equal to root under this much. So you will get the radius to be this value. Correct? Okay. Any doubts here? So basically the upward force, since the or the main thing that you have to understand is, since the droplet is moving with a constant velocity, therefore the upward force, that is F drag minus, sorry, plus your F of buoyant should be equal to weight. Avloda. Okay, and since the buoyant force and the weight, both of them have their values as volume multiplied by density, we are bringing both of them together on one side. So Fd is equal to weight minus Fb. Understood? The only reason why we are writing it like this, because both the W and the Fb are in the form of your volume times density of oil times G, and volume times density of air and G. That is the reason why we wrote it like this, so that we could take the density out common. Understood why they did that? Okay. Okay, next. Okay. When the electric potential difference between the plates is adjusted to 1750 volts, the drop is brought to rest. The distance between the plates is 1.2 centimeter. Determine the charge on the drop. State the answer in terms of elementary charge. Okay, now basically what is happening here? Now there is another force. Okay, what is happening here? The drop is brought to rest. When the drop is brought to rest, what happens? Your the electric force, okay, the net force on the drop is again zero, but the drag force is replaced by, why is the drag force replaced by the electric field force due to the electric field? Because drag force only takes place if you have a movement in the fluid, but right now it is not moving with a constant velocity. It is at rest. When you are at rest, you don't experience any drag force. Understood? When you are at rest, you don't experience any drag force. So basically the electric force should be equal to the downward force, that is this whole value, 4 by 3 pi r cubed density of oil minus density of air, the whole multiplied by G. Okay, now we know that force is equal to what? Force is equal to field times charge, and field is equal to what? V upon D is equal to. So Force due to electric field is equal to how much? V upon D times Q. So we know the voltage. We know the voltage to be around how much? Yeah, 1750 volts. We know the distance to be 1.2 centimeters. Okay, so we know the distance. We know the charge also, right? What is the charge? What is the charge? What is the charge? Oh, determine the charge. We have to determine the charge. So Q is unknown. Okay. So we can figure. We have already figured out the value of this whole thing. 4 by 3 pi r cubed density of oil minus density of air times g, because now we know the radius, right? We know the radius. We can figure out this whole value. So basically we can write Fe is equal to Vq upon D is equal to 4 by 3 pi r cube density of oil minus density of air times G, right? Okay, so basically only this particular value is unknown, but rest of everything is known. So can we figure out the answer? Okay. Okay, fine. Let's move on to the next question. Okay, I don't have to solve it, right? Just formula based. Okay, I saw your assignment, Akshay. Just like this, whatever questions that we do in class, you will do it separately and show it to me. Okay. Yeah. Next one. Now, an oil drop of mass 3.3 into 10 to the power minus 14 kilograms has an excess of 10 electrons. Has an excess of 10 electrons means what, Akshay? It means that it has a negative charge of 10 electrons. Negative charge of 10 electrons. The drop is suspended at rest in a uniform electric field in vacuum. Calculate the magnitude of electric field strength and state its direction. Okay, now if you want to suspend something in the air, you have electrons. Okay, you have electrons. Okay, let's look at this. Now we know that gravity always pulls everything towards the ground, right? So these are two plates here. These are two plates here. This is the oil drop. This is the oil drop, and there is a force that is being attracted onto this oil drop in the downward direction called mg. Am I right? Okay, next. Now, there should be a force because it is suspended. The drop is suspended at rest in a uniform electric field. There should be a force upwards, force due to the electric field. Okay, now, what is the charge on this drop? The charge on this drop is negative because it has excess of electrons. The only way it will be suspended is if there is negative charge in the downward plate. Then only this negative and this negative will repel each other, right? If there were a positive charge here, won't it get attracted downwards? Okay, so there has to be positive charge on this plate. So where will the direction of the magnetic electric field will be? Electric field starts from the, where does the electric field originate and where does it go? Akshay, simple question. Where does the electric field originate? Does it originate in the positive or in the negative? It originates at the positive and goes towards the negative. This is the direction of the electric field. Okay. Now, for the oil to get suspended, what should happen? Fe should be equal to mg. We know the value of m, we know the value of g, right? Okay. Now, Fe can be written as electric field, that is the force per unit charge multiplied by charge. So how much is the charge? 10 electrons should be equal to mg. So electric field should be equal to mg upon 10e. Therefore, mg is how much? 3.3 into 10 to the power minus 14. Take the answers out. Take the answers out in your phone. 3.3 into 10 to the power minus 14 into, let's call it 10 upon 10 into 1.6 into 10 to the power minus 19. Okay, so this 10 and this then gets cut off. Okay, this 19 when it goes up, this 16 twos are 32 approximately. So 2 into 10 to the power minus 14, and this 10 to the power minus 19 goes up, it becomes 10 to the power of 5. The electric field is 10 to the power 5 newtons per coulomb. Is it correct? 2 times 10 to the power 5 newtons per coulomb, and the direction is from where to where? From the bottom, sorry, from the top to the bottom. What did they write? They wrote top to bottom only, right? Vertically downwards. Yeah, it's vertically downwards. It's correct. So did you understand how to do this? Okay. Now, Akshay, all you have to remember is if it is stationary, then there is no what? There is no viscous drag. If it is stationary, there is no viscous drag. If it is moving with a constant velocity, then also the net force is zero. But now what is happening is the value of that thing, what do you say? The viscous drag does not become zero. In Millikan's experiment, a negatively charged oil drop of radius 1.8 micrometer R is given to us, and mass 2.1 into 10 to the power minus 14. So mass is given to us. Okay, is at rest in space between two parallel horizontal plates like this. Okay, two parallel horizontal plates. The distance between the plates is 9 millimeter. So this comes out to be 9 into 10 to the power minus 3 meters. Okay, and the potential difference is 1.9 kilowatts. Okay, so this distance is coming out to be potential is equal to 1.9 kilovolt. That is 1.9 into 10 to the power of 3 volts. Okay. Now potential difference is also known. Now what have they asked us to calculate? Calculate the charge on the oil drop given the answer, giving the answer in terms of E. Ignore the buoyancy force. Okay. We are supposed to ignore the buoyancy force. So weight should be equal to, not, there is no drag force here because it's at rest. Electric field force. Yeah. Therefore you should say that force due to electric should be equal to mg. Okay, now we can write this force as eq should be equal to mg, or you can write it as v upon d times q should be equal to mg, which gives us mg multiplied by d upon v is equal to q. Okay, yeah, so let's actually try to solve this. So mm, let's see, you have mg, that is 2.1 into 10 to the power minus 14 kg multiplied by uh, g, right, multiplied by 10 multiplied by distance is 1.8 into 10 to the power minus 6. No, wait, why did they give us the radius? We don't need the radius, right? For now we don't need the radius. Okay, multiplied by 9. Yeah, 9 millimeters multiplied by 9 into 10 to the power minus 3 upon 1.9 into 10 to the power of 3. Okay, so this will become equal to 21 upon 19 multiplied by 10 squared, 10 to the power minus 14. This and this I have used up. This and this I have used up. So basically 10 to the power minus 14, 21, 20 to the power minus 3 becomes minus 17 multiplied by 10 to the power minus 17, and if I take this up it becomes 10 to the power minus 19. If I take this thing upwards it will become 10 to the power minus 2, so I'll get multiplied by 9. So 21 multiplied by 9 upon 19 into 10 to the power of minus 19. So 9 2s are 18, 2 approximately 10. So this becomes equal to 10 to the power of minus 18 coulombs. So approximately 10 to the power minus 10 to the power minus 18, and then like basically I have to divide this by 1.6 into 10 to the power of minus 19. When it goes up it becomes 10. 1 upon 10 upon 1.6 becomes equal to how much? 16 6 are all approximately 6 electrons. Is the answer correct? 6 electrons. Approximately you will get 6 electrons. Okay. So no need of using calculators. Sometimes rough calculations works a lot. Okay. Shall I erase this? You understood this, right? Anyways, okay. I'm going to erase this. Okay. The charge on the drop is changed and the drop starts to move downwards, reaching a constant speed of 0.11 meters per second square. Oh, now we should use the viscous drag. The electric field strength remains unchanged. Determine the new number of excess electrons on the drop. The viscosity of air is 1.8 into 10 raised power minus 5 Pascal second. Okay, so we have to ignore the buoyant force in this whole question. That's what they have said, right? Ignore the buoyant force. We should ignore the buoyant force. Okay, so can I? Yeah, yeah. Okay. No, because see, if they had asked us to, if they had asked us to calculate the buoyant force, they would have given us the density of air, right? We don't know the density of oil or the density of air or the density of anything, so buoyant force is ignored. So we can write it as force due to drag should be equal to the drag force. The drag, mm, yeah, of course. The drag force plus force due to electric field should be equal to the weight. Okay, so we know the mass now, 6 pi nRV multi plus uh, what did we calculate? Okay, yeah, we can calculate the force as uh, V upon D multiplied by Q, right? V upon Q, this is what force is, right? Electric field times charge. Electric field is voltage upon, okay, is equal to mg. So okay, so we need to calculate the charge again. We need to calculate the charge again, right? Okay. So uh, no, we have to find the excess electrons. No, we just subtract it again. They added some charge to it. So V multiplied by D upon Q should be equal to mg minus 6 pi n r V. So this whole thing Q will be equal to this whole thing mg minus 6 pi n r V multiplied by D the whole upon V. Clear? So what is mg coming out to? So 2.1 into 10 raised to power minus 14. So q is equal to 2.1 times 10 to the power of minus 14 multiplied by 10 minus of 6 multiplied by, will it help? 3.14 multiplied by 6 pi n is 1.8 into 10 to the power of minus 5 n. R is coming out to be 1.8 multiplied by 1.8 micro into 10 to the power of minus 6. Oh my god, it's going to be huge. Multiplied by 6 pi n r v is 0.11. Okay, 0.11 the whole upon one. Huh? Oh yeah. We have to. Oh, they don't leave an inch. Everything is crazy. Okay, fine. So 0.11 into 10 to the power of minus 3 meters per second multiple 6 pi n rb multiplied by 1.9 into 10 to the power of 3 multiplied by 1.9 into 10 to the power of 3, and there is a d also, right? D is how much? 9 millimeter. 9 into 10 to the power of minus 3. Okay. This is going to take a lot of time by doing by hand. Okay. Yeah. You put this in the calculator. See what you get. What is the answer? So this is coming out to be, Q is coming out to be 8 electrons, right? Oh, you have to then divide, if you want to find it in electrons, then you'll have to divide by 1.6 into 10 to the power minus 19 also. So it is coming out to be 8 electrons. Okay, so then Q dash is equal to 8 electrons. Therefore, the excess electrons will be how much? 2 electrons got added extra. So the answer is coming out to be 8 electrons. Okay, 8 excess electrons are there. There is a total of 8 excess, that's it, 8 excess electrons are there. You don't need to subtract or anything. Just 8 excess electrons are there in the oil drop now. Understood? Okay, next one. So, electric potential. Okay, in topic B5, the quantity electric potential difference was. Oh, this is not part of the syllabus? Okay. Okay, let me just see what is part of the AHL. This is not that much of a hard topic actually. Okay, anyways, AHL we can ignore it. Okay, because that's not part of your syllabus, so we can ignore it. Let's move on to the next topic, magnetic fields. Okay, so the repulsion between the like poles of two bar magnets is a familiar phenomenon. Impressive forces act between magnets of even quite modest strength. Moderate materials are used in tiny neodymium magnets less than 1 centimeter in diameter and a few millimeters thickness that can easily attract another ferromagnetic material through a significant thickness of non-magnetic substances. Magnetism is another field phenomenon. A magnetic field exists at a point when a magnetic force acts on a magnetic pole. In practice, a pair of poles placed at that point. As with electrostatics and gravitation, magnetic fields are visualized through construction of field lines. Okay, so magnetic field is also a type of non-contact force only. Okay, it is a type of non-contact force. Okay, it is usually made up of neodymium and all that other stuff. Okay, now we have to now understand how to visualize the magnetic field lines. Magnetic field lines have similar but not completely identical properties to that of electric field lines. Magnetic properties of field lines are as follows. Magnetic field lines are conventionally drawn from the north seeking pole to the south seeking pole, or can be closed lines that do not end at a pole. The line direction represents the direction in which a north seeking pole at that point would move. The strength of the field is shown by the density of the field lines. It is shown by the density of the field lines. Lines drawn closer together imply a strong field. Okay, same logic. When you have the field lines close to each other, you get to have a very strong and powerful field. Clear? Okay, yes. The field lines can never cross each other. Again, we know this. Why can't they cross each other? Because if they try to cross each other, then what will happen? There will be two different directions at a single point, and that cannot happen. Okay, so the field lines act as though made up of elastic threads. The system acts as if to make the field lines shorter. The field lines always like to remain shorter. Okay, now they move in an elastic manner. Okay, they move in an elastic manner. If you move the magnets far away, they become basically more longer, but if you move them closer, their magnetic field lines will become shorter. Okay, so basically they act as elastic, what do you say, rubber bands. Okay, when you move them far away, their magnetic field is also stretched. When you move them closer, the magnetic field just becomes shortened. Okay, now these assumed properties suggest ways in which the system can change to reduce the total length of the lines. Now, this can be imagined as a reduction in the total energy stored in the system if there is a fixed energy per unit length of the line. Okay, so what is happening here? Okay, so the field lines are elastic. They want to become shorter and shorter. Okay, they want to become shorter. Okay, and the only way to make them shorter is actually making the poles come closer. The poles have to come closer. So basically we are talking about an attraction of alternate, basically two different types of poles. Okay, now what is the last line? These assumed properties suggest ways in which the system can change to reduce the total length of the lines. This can be imagined as a reduction in the total energy stored in the system if there is a fixed energy per unit length of the line. If there is a fixed energy per unit length, then what happens basically? Yeah, if there is a fixed energy per unit length of the line, let's actually move on. Okay, now, okay. So it can be confusing when you are talking about magnetic poles due to difference in the notation. This parity arises from the original observation of magnetism when early navigator noted that a lodestone suspended from a thread would align itself. A lodestone suspended from rest would align itself north-south. When we write magnetic north pole, what we really mean is the magnetic pole that seeks the geographical north pole. It is seeking the geographical North Pole. Why is it seeking the geographical North Pole? Because at the geographical North Pole, we have the South Pole of the Earth. Okay, that is the reason why what happens when you have a North Pole like this. For example, if this is the Earth, if this is the North Pole, what happens? It will always align itself with the North Pole. Why? Because with the aligned North Pole, what ends up happening? Huh? This North Pole gets attracted to the South Pole of the Earth. This is the South Pole. Look at this. So in the northern Americas, in Russia and all of those places, you have the geographical, you have the South Pole. Okay, this is the South Pole and this is the North Pole. That is the reason why every single magnet would align itself in the north-south direction so that it gets attracted to each other. Okay, like this. See, if you have a pole like this is south, this is north. So another magnet would align itself as north and south. So the distance between the North Pole and the South Pole would be small enough. Okay, that is what's happening here. Okay, now we often talk loosely about a magnetic North Pole pointing to the North Pole. A misunderstanding can occur here because we also know that like poles repel each other and unlike poles attract each other. We could end up with the situation that a magnetic North Pole is attracted to the geographical North Pole, which seems wrong in context of the two poles repelling. In this book, we talk about the north-seeking pole, meaning a geographical north-seeking pole, and a south-seeking pole, meaning a geographical south-seeking pole. On the diagram of magnets, north always means geographical north-seeking pole. S always means the geographical south-seeking pole. Figure 31a shows the magnet that must effectively be at the planet's center to give rise to this observed magnetic field patterns of the Earth. Right? There is a south pole at the north pole of the Earth, and there is a north pole at the south pole of the Earth. Understood? Next. So that is the reason why, see, if you even have a magnet like this, okay, the magnet, this is the North Pole, the magnet would align itself with the geographical North Pole. Understood? Okay. Okay, next. Figure 31a shows the magnet that must effectively be at the planet's center to give rise to the observed magnetic field patterns of Earth. Figure 32b shows the patterns for a single bar magnet, and figure 32c and 32d give two arrangements of a pair of bar magnets of equal length. In the magnetic pair, notice that the characteristic field patterns when two opposite poles are close, figure 32c, and when the two north-seeking poles are close, figure 32d, when two north-seeking poles are close, alternatively two south-seeking poles, there is a position where the field between them is zero. When two opposite poles are close, the field lines appear to connect the two magnets, forming a pattern like that of a single bar magnet. See, you have one south pole and one north pole like this, and the field lines are going like this. See, the field lines are going like this. It just behaves like a single bar magnet. Similarly, when two different poles, sorry, when the same poles are brought next to each other, what happens? The field lines basically curve away in such a way so as to show that they are trying to repel each other. So you are left with an empty electric field. There is no empty magnetic field. There is no magnetic field at the center. Clear? Understood? Yeah. So, okay. Yeah. So, in terms of the rule for the field lines, poles moving close to each other in figure 32c will shorten the field lines between the poles. This implies that magnets will do this if they are free to do so, as it is energetically favorable. So, that is the reason why when two alternatively opposite poles, one north pole and a south pole, are brought closer to each other. When they are brought closer to each other, what happens? There is because there is one field originating from here and there is another field originating from here, the fields want to shorten their length. They want to shorten their length. So what happens? They will try to bring themselves closer to each other until and till the point where they are not physically in contact with each other. When they are physically in contact with each other, then the length of the field line is the shortest. The length of the field line becomes the shortest, and that's what the this magnetic field wants also. The field lines want to be as short as possible. Okay, so when you bring two poles, okay, one north and one south, they basically will produce field lines from the north pole and terminating at the south pole, and this will allow them to basically want to become shorter and shorter and shorter. Okay, thus at the end they will basically both be stuck to each other. Clear? Okay, let's move on. So this is what they have written at the end. See, this implies that magnets will do this if they are free to do so, as it is energetically favorable. Okay, that is the reason why opposite magnetic poles always try to attract each other. Okay. Mm, okay. Can we continue the magnetic field pattern in the next class? Okay. Shall we? We'll finish this in the next class. Okay. So I'll just end the video now. Okay. If you like this video, please do like, share, and subscribe, and wait for the next video. We'll finish this chapter in the next video. Thank you and have a nice day.